So after doing a whole bunch of grade 11 like kinematics review with a basic formula, the DTV, the VAT, hopefully got some memories going with that. We're going to see if we can expand your ideas, your knowledge of sort of how that stuff works a little bit. Now, technically, this isn't really new. It's just like a different viewpoint of where these ideas come from and how things actually link together better in order for you to have a better understanding of what's going on with basic kinematics type stuff. Now, what we're going to do is we're actually going to kick back to basic grade 11. And when you guys started grade 11 kinematics, you guys looked at kinematic graphs. That's typically where we start. We had the DT graph, VT graph, and you guys found slopes. But we're gonna expand on that a little bit. Okay, so I'm gonna kick back to basic kinematic graphs. And in grade 11, typically you start with DT graphs. That's typically what we have. So, for example, you'd have something like this, a DT graph like this, and there you go, something like that. And of course, what you guys did, was the slope was equal to the speed. And then the next thing we sort of kicked into was a VT graph, something like this. And of course, from this guy, the slope gave you your acceleration. So these are the types of things that you guys worked on last year. So let's see if we expand on this from grade 11 for grade 12, because then we can leak into some other ideas as well. Now, when we talk about motion graphs and all that kind of stuff, the key value for motion is this guy right there, the speed. And when you think about moving, you think about speed. Things have speed when they're moving. Of course, they travel a distance and they, we're using acceleration to get there. They don't have to have acceleration to be moving. But if you're moving, speed is the one thing that that's like your property. I mean, distance isn't actually, like, you travel a distance, but the distance isn't actually about you. It's actually about the stuff that's sort of being left behind, so to speak. So we're going to start by just using a basic VT graph. So let's go back to a VT graph for a second. Let's just take the basic fundamental VT graph. The simplest one we could have would look something. Well, that's just messy. The basic fundamental we'll have, I'll even use my fancy tools here, would be a straight line going across. So this is like the most simplistic VT graph you can have, just straight line going across. So if we have something like that, I'll change the color. Why not? There we go. So if we have something that looks like this, of course you guys know this. We have we got a constant. There's a constant speed. There is no acceleration. And how do we know that there's no acceleration? Well, because the slope would be equal to 0. So we've got this thing moving with a constant speed. There's the slope of the line would be 0, so there's no acceleration. So if you're moving at a constant speed, you don't have an acceleration, that's fine, but you are covering a distance. Like, you're actually moving from one place to another. So if this VT graph, and this VT graph does represent a situation, it represents the speed, it represents the acceleration, and that's the slope is equal to 0. What about the distance? Okay, you got the V, you got the T, you got the A. What about the distance? Is this also represented within the graph? Okay, well, it is. Distance is in this graph somewhere. So where is the distance represented in this graph? The slope is the acceleration, and that's 0. So what about the distance? How is the distance represented within this graph? Now, there's a couple ways we can go about this, sort of figure this out. But let's go back to simple, basic grade 11 physics. You're moving at a constant speed. If you are moving at a constant speed and you are worried about distance, how do you find distance? Well, distance, of course, would just be, good old-fashioned DTV, no big deal. And of course, the V is average or constant. In this case, it is constant, so it's no problem. So distance is T times V. Okay, so that's the basic formula, but how is that represented graphically? Well, let's go to our graph. we have a t value, we have a v value, obviously. I mean, here's our time, and I'll bring up my line tool here. Here's our time over here. Okay, we went from there to there for time. Okay, we went from here to here for v. So there's my time, and there's my v. So how is that represented on the graph? Well, that line at the bottom, that t1, is actually the same as this line up, is actually the same as this line up here. These two are actually the same. And this is actually how high up it is over here. So I'm going to clean that up again a little bit. There we go. So if I could sort of like redraw, I could take that line at the bottom here, and it actually also belongs up here. Those two lines are the same. And this line over here, I can also move over here. And as soon as I do that, hopefully you can recognize sort of what's going on here. I've created a rectangle. There's actually a rectangle right here. Okay, there's a basic rectangle. Now, the dimensions of that rectangle are the time and the speed. And if you multiply the two dimensions of the rectangle, you, of course, get the area of a rectangle. And that's literally what we've done here. This dTV is actually the area of the rectangle inside of this graph. Okay, and that's what actually is happening with the dTV. It's actually the area of the rectangle. So if you have a VT graph, the distance traveled is actually this area right here. Okay, so it's kind of nerdy, mathematically cool, but that's what you guys are doing. So every time last year when you guys calculated dTV, every time you did that last year, you were actually calculating the area of a rectangle. Now, of course, you go, hey, wait a minute, the speed isn't always constant. What if it's the average? Well, that's also kind of nerdy, mathematically cool. If we have a VT graph that looks like this, and it instead is something like this, where the V is not constant, and you apply dTV to it, what did you guys do last year? Well, you guys didn't use the final V at the top. You didn't use, the final V at the top. What did you guys use? You guys would use the average. And of course, the average is right there. So when you guys would use dTV with the average, because of course this can be average sometimes, what you would do is you'd actually modify it. So instead of using the V up here, what you guys would actually do is use the average V, and that average V then just makes the rectangle look something like this. And then graphically what happens is this top part of the triangle is sort of cut off. It actually rotates and flips and fits perfectly in there to once again make a perfect rectangle. So when you guys would do dTV and this was an average V, what you're actually doing is you're finding the area of a triangle and you're sort of forcing the triangle to turn to a rectangle. Okay, so you actually you sort of actually make a rectangle out of it. No, actually you find the area. Okay, so you find the area. Now, the other way you can look at it, of course, is if it was a triangle. I mean, if you have the area of a triangle, if you find triangle area, you guys know this, that's base times height divided by 2. Well, the base of my triangle was t, my height was my final v, and then you're dividing by 2. And right here again, that is, well, if you're starting at 0 and you cut the final v in half, that is average v. So it's t times average v again. It's all the same thing, coming from different perspectives. Okay, so every time you guys have done dTV, you've been finding the areas of rectangles, not even known it. Now this applies to any formula that you want. Any formula that you guys have ever used that multiplies two things together will give you an area. For example, if you do a mass times acceleration graph, well, that area in there, that area is going to be force, because force is mass times acceleration. Okay, that's where it can come from. All right, even other ones that you guys have done before. For example, if you do a density times volume graph, that will give you the mass, because density times volume is mass. And this applies to any formula where you're multiplying two things together. That's what you're actually doing, is you're actually finding the areas of the graphs and then putting them together. Okay, so let's sort of show you some other stuff with this as well. So I'm just going to draw another little graph here. I'm going to draw a VT graph in the middle, and we're going to do something like this. And I'm going to draw it in the middle for a reason, because over here I am going to draw a DT graph, and over here I'm going to draw an AT graph. And if the VT graph was a line that looks like this, the V is changing, the DT graph would look something like this, and the AT graph, the V, constant slope, would look something like this. Okay, so when you guys were working with this type of stuff last year, of course, the slope in a DT graph gives you your V, the slope in the VT graph gives you your A. So if you find the slope of the DT graph, that would give you your V value. And then once again, you find the slope of the V graph, and that would give you your acceleration. Well, you can do the exact same backwards. When you're going towards the right, you're actually using slopes. But to go backwards, this is where the areas kick in, because the area of a VT graph gives you your distance. And the same thing happens with acceleration and time graphs. If there's a rectangle here, and acceleration times time, this rectangle, that will give you your V's, more specifically your change in V's. So the area for this goes back the other way. So slopes will take you in one direction, and then areas can be used to take you back. Now in calculus, this is derivatives and integrals and that kind of fancy schmancy math. That's what it's based on. But that's how these things all sort of lead together. And that's one of the reasons that the VT graph is like the core kinematic graph, because from the VT graph, you can find distances or accelerations. You can go in either of those two directions. If you're at acceleration, you have to sort of jump over to get to D. You got to go a couple steps. Same thing for D to acceleration. But the VT graph is the core graph because it directly links to both the distance and the acceleration directly. And that's what makes VT graphs so awesome compared to the other two. All right. Now, of course, reality kicks in for this type of stuff as well. Graphs are not perfect, especially experimental graphs. They're not perfect. They're not, straight lines and curves and beautiful shapes all the time. And that's where other stuff kicks in. So even if you have something, maybe, you have a VT graph that, it's not just one shape. Maybe it does this, and then maybe something like this, and then something like this. Maybe you got something like this going on. Well, you would then find the area. If you want to find how far it goes, you find the area. And you might be able to recognize what's going to go on here, but you can cut this into shapes. And when you have sort of like, if you've got like multiple sections going on, this is where you use composite areas. And this is where, like in math class, when you guys had like weird geometry shapes, and you had to find like the composite areas and break shapes into different sections of triangles, and you'd add them together. That is what that is for. It's for this type of thing. So when you have multiple sections, you can use composite areas, where I'd have the area of this triangle, then this area, this rectangle, then this rectangular square, and then this triangle, and you would add the areas together. So then, of course, your total area would equal your change in D. Okay, so that is one of the key things composite area is for in math, is to do stuff like this. Even if you have an acceleration graph that looked like that, you'd add up all the areas to find out what the overall change in V was. So that is where this type of stuff kicks in. Now, of course, you can also get even more realistic. Graphs often they're not necessarily smooth, and they'll do like weird things or whatever, stuff like this. Now, this is entirely different because there are no perfect shapes, there are no perfect anything with this. And this is where some other stuff kicks in, where what you'll do is you end up, I'll try and do a rough version here, is this is where something else you guys have done before, where you do stuff like this, where you make a grid type system. Okay, hopefully this looks sort of like familiar from like math class and stuff, that where you've done this type of stuff. stuff like this, and you make a grid system. And what you need to do is then count the boxes, and you add up the boxes. So when you have something like this, which is really, really strange, sometimes what you do, especially when you look at like reality, of course reality sucks, there's no straight or smooth lines in reality. I mean, that's just the way it is. So what you do is use a grid to actually break up the areas, and each one of these boxes will represent, hopefully, like you do this like in elementary school, junior high, and stuff like that. It kicks in high school as well, but that's where this comes in. So, like you count, here's a full box. There's 1, 2, 3, 4, 5, 6 full boxes, and then you start putting partial boxes together, like this box over here and this box over here, sort of combined to make one. And you sort of add up the boxes in order to estimate the distance as best you can. And you sort of use a grid to break up the areas of that, and then you add up the boxes in order to actually estimate the total. And this is where especially calculus really kicks in later on with integration. That's the idea behind integrals and integration, which some of you guys may have already started into, but you will get into later on if you want. That's what they do. And of course, the smaller the boxes are, the more accurate your adding will be. And basically what calculus does is it makes the boxes infinitely small in order to make it infinitely accurate, is basically what happens. So it's really neat, especially, when you're doing this graphically. It can be kind of labor intensive, but, if you do a simple grid, like maybe this is like 1, 2, 3, 4, maybe this is like 2, 4, 6 or something like that. This box is 2 by 1. So if this is 2 tall and this is 1, every single box, 1 times 2, that represents 2 meters is what that little box represents. So then I just count up the boxes. Each box represents 2 meters. And multiply it, and I got my total distance. And again, when you're doing it rough and graphical like this, it's just an estimate. That's all it is. But that's how this type of stuff works. And again, this applies to any formula you've ever used where you just multiply 2 things together. That's where it comes from. And typically, any 3-term formula, what are you doing? Well, you either multiply 2 things together to get an area, or you divide 2 things together to get a slope. That's literally how all of this type of stuff works. Even if you go back to good old-fashioned grade 9, and in electricity and grade 9 science, as well as like if you took electronics, one of the formulas that you have is Ohm's law, and Ohm's law is R is equal to V over I, or voltage divided by current. Well, since you're dividing those two, that is a slope. If you have a voltage current graph, it looks like this, and the slope will give you your resistance. But if you would do a current times resistance graph, and you multiply the two together, it would actually give you the voltage, because voltage is equal to I times R. So again, this applies to any 3-term formula, whether it's in physics, chemistry, math, it makes no difference. Formulas, especially 3-term ones like this, which are really fundamental and simple, are about 2 things: multiplying to get area, or dividing to get a slope. And that's more of a fundamental basic idea behind what you guys are doing last year. So last year, when you guys would do delta V is A times T, you calculate an area. When you guys did delta V over delta T, you calculated a slope. When you guys calculate even delta T is delta V over A. That's the slope of a delta V over acceleration graph. So like that's how this type of stuff works. Okay, even if you go to some other stuff you guys did last year, if you do speed is frequency times wavelength for waves, remember that one? If you do a frequency wavelength graph, the area is the speed of the wave. I mean, it connects to all of them. Okay, so that's just a little more basic idea behind how the real importance of graphs. And again, sometimes why do you use graphs so much? Well, graphs are really important. Not only do they give us slopes and things like intercepts and stuff like that as well, but they also are the source of areas, which allows us to get sort of like the other half of the formulas going. So really, it's kind of strange. Like pretty much every calculation you guys have done involves a slope or an area of some way. And this is sort of how that all sort of works together. Okay, so we'll go back to basic DTV, VAT, FMA, all that stuff, even friction. Okay, friction is mu Fn. You take a coefficient of friction times normal force graph. The area is the force of friction. It applies to any graph like that. Okay. So this is just like, we're not going to go hardcore into all this type of stuff, but this gives you an idea of how this stuff actually all sort of links together better. And if you're ever given a graph, especially a graph that looks, kind of wavy or curvy, or even a composite shape one, and you need to find, the value that comes out of it, now you know how that type of thing. You talk about composite areas, whether it's perfect shapes like this guy right here, you just got to add up the shapes, like in, junior high, grade 9 math, or something like this where you have to make like a grid system and just count up the boxes as best you can and average it out. That's generally the way it works. Okay, so that's a more of a complete idea of where how graphs really kick in and the importance of graphs for physics and how they link into all the stuff that we do.